Okay, let's jump in here with some examples for stoichiometry. In photosynthesis, plants convert carbon dioxide and water into glucose according to the reaction that is shown right there. I'm not going to read through that whole thing. Suppose you determine that a particular plant consumes 37.8 grams of CO2 in 1 week. Assuming that there is more than enough water present to react with all the CO2, what mass of glucose in grams can the plant synthesize from CO2? So this is the same basic idea that we had before with this question here, only now it's a different reaction. So we're still going to go through the same process of starting with the mass of one thing and getting to the mass of something else in the same reaction, just going through these 3 steps here. So we're starting with 37.8 grams of CO2, and we are going to a mass of glucose. That's our final point, is going to be glucose. So we're going to use, again, molar masses for these 2 steps, and then we're going to use the ratio from the balanced chemical equation for this step. So the first one here, we need the molar mass of CO2, which I believe is 40. Let me see here. So we have 16 plus 16 plus 12, 44. That's what it is. Okay. So 44 roughly. Technically it's like 44 point, I think it's 0.01. So we'll just go ahead and go with that. 44.01 grams of CO2 for every 1 mole of CO2. So that's this first step here. So now that we have moles of CO2, we're going to use the ratio. So the ratio, again, is just the coefficients. So we have 6 CO2 used up for every 1 glucose that is used up. So we have 6 moles of CO2 for every 1 mole. I'm just going to call it glue, so I don't have to write out that whole thing every time. So it's a 6-to-1 ratio, and again I'm putting the 6 CO2 on the bottom because I needed to cancel out here. So far my grams of CO2 have canceled, and my moles of CO2 have canceled. And so then my last step here, so I've done this step now, so my last step is to convert from moles of glucose to mass of glucose. And so I need to find the molar mass of glucose. So the molecule is shown right here. Carbon is 12.01, hydrogen is 1.008, and oxygen is 16 grams per mole. So I have 6 times 12.01 plus 12 times 1.008 plus 6 times 16. So glucose has a molar mass of 180 and we'll just go 16 grams for every mole. So again here my moles of glucose have now canceled, leaving me with grams of glucose. So if I do the math, 37.8 times 180.16 divided by 44.01 divided by 6, that leaves me with 25.8 grams of glucose. So, way to go, little plant, making some sugar. Okay, let's look at another example here. So this one is going to be just a little bit more complicated because we're going to have an extra step. So this says sulfuric acid is a component of acid rain that forms when SO2, a pollutant, reacts with oxygen and water according to this simplified reaction. The generation of electricity used by a medium-sized home produces about 25 kilograms of SO2 per year. Assuming that there is more than enough oxygen and water, what mass of sulfuric acid in kilograms can form from this much SO2? So the extra step that we're adding on here is that the mass that we're starting with and the mass that we're ending with are no longer grams. So we're going to start and end in kilograms instead of grams. So all we're doing really is just we're adding on a gram to kilogram conversion at the beginning and at the end, which is not terrible. We know how to do that. We know how to convert between grams and kilograms. So let's go ahead and get to it. So if we're starting with 25 kilograms of SO2, we're going to go ahead and convert that to grams first. So we have 1 kilogram is the same as 1,000 grams. So my kilograms are now canceled out. Now I'm here where I started before with grams of my material. So I can go ahead and use the molar mass of SO2. Sulfur, if I remember correctly, is 32, I believe, 0.02. And oxygen is 16, and we have 2 of those. So this is going to be 64.02 grams for every mole. Now we need our ratio, and based on our balanced chemical equation here, our ratio is actually just 2 to 2, which is the same as saying 1 to 1, but I'm going to go ahead and put the 2's in there just so it matches what's in the balanced chemical equation. So for every 2 moles of SO2, I will have 2 moles of the sulfuric acid. So the moles of SO2 were on the bottom because I needed to cancel out the SO2 that was on the top here. Okay, so again, my grams here are gone, moles of SO2 are gone. So I have moles of H2SO4, so right now I am here. So I converted out of kilograms into grams. That was my first conversion factor. Out of grams into moles. That was my second. And then I used my balanced chemical equation to convert to moles of the second material, which is the sulfuric acid. And so now I need the molar mass of sulfuric acid. So I have the structure right here. Remember, hydrogen is 1.008, and I have 2 of those. And I have 32.02 for the sulfur, and then 4 times 16 for the oxygen. And that leaves me with 98.0, and we'll just go 0.4 grams. Alright, so now I am here. But the question did specifically ask for the mass in kilograms, so I do need to do one last conversion factor before I wrap up the math. So there are 1,000 grams in 1 kilogram. So my moles of H2SO4 have canceled, grams of H2SO4 have canceled, leaving me with kilograms of H2SO4. And so if I do all this math, 25 times 1,000 times 2 times 98.04 divided by 64.02 divided by 2 divided by 1,000, I get 38 point, and let's see, I'll round to the 3 here, 3 sig figs. So 38.3 kilograms of sulfuric acid. Now, one thing you might notice here is that because we started in kilograms and ended in kilograms, these two conversion factors canceled each other out. They ended up not having an effect on the math. Really, the only thing that had an effect on the math was obviously the amount we started with, and then the two molar masses, because the ratio here was also 1 to 1, so it didn't actually have an effect on the math either. But that will not always be the case. So even if you're pretty sure that you won't end up changing the math with these gram to kilogram conversions, I would suggest go ahead and put them in there just to be safe. It's better to spend an extra 15 seconds on that and be sure that you're doing it correctly than to make an incorrect assumption and mess up on a problem like that. Alright, I think we'll go ahead and call it here for this video. Just a video with a couple medium to long example problems there. And the next one we're going to pick up with limiting reactants and theoretical yields, which is where we'll actually start talking about doing these types of reactions in real life, where we actually do have a material that it's going to run out at some point. And so that's what we'll talk about next time.